All right, so I have the distinct pleasure of introducing Rob Sherwood. I met Rob, I think it was 2008, when he came fresh out of a PhD. Is that true? Yep. To join Deutsche Telekom Labs to do OpenFlow-ish things. And since then, he's done all kinds of cool systems for both testing OpenFlow, things like OFTrace, benchmarking OpenFlow, things like CBench and OFLOPS. It's on.
He met me.
He met you, OK. And FlowVisor, which is the system he's going to explain now. So I'll turn it over to Rob.
Thanks, Brandon. Morning, everybody. Thanks for giving me a chance to talk to you about some of this virtualization stuff. A lot of you probably know a lot about virtualization. It probably means everything to everyone, and we have a reasonable cross-section of everyone here. So I'm actually going to spend a little bit of time trying to talk about what I mean by virtualization, some of the use cases that go along with it, some of the things that come out of SDN as a result of this. I'm going to quickly move, because this is an engineering tutorial, from a high-level, hand-wavy what is virtualization to a very solid case study in a specific tool that I spent 2 or 3 years working with Brandon and others developing called the FlowVisor. And I'm going to get into the FlowVisor's architecture, this thing that we're going to call opt-in, how we allocate resources in these virtual networks, and specifically this resource that we call FlowSpace, which is the set of headers that you're allowed to control. And I'm going to actually talk about deployments. For better or for worse, people have taken my code and are deployed in real production networks, and I'll touch briefly upon what those are and what those people are thinking. And then at the end, I'll kind of pop out of this use case and maybe wax a little bit philosophic about virtualization in general and what this means in an SDN world. So all of you have probably used some level of network virtualization. Whether this is VLANs or whether this is everybody sharing a network, bandwidth sharing, TCP backoff. One could make arguments, and I have at various points in my life, that all of these things are flavors of network virtualization. Just to get everybody on the same page, I'm going to throw out just some terms that honestly I've made up for the purpose of this talk, just to get everybody on the same page of what I mean with this. I'm not really trying to start any arguments. I'm not trying to start any religious wars. I'm just trying to make a useful conversation out of this. And so one of the first types of network virtualization that you think of is what I call topology virtualization. That is creating links, creating nodes, changing who's in the same broadcast domain. These are all kind of functions of topology. And this is the type of network virtualization that most of you are probably familiar with. So a virtual link is really a tunnel. You're creating a link between something that doesn't exist. Broadcast isolation, you can do this with VLANs. Virtual nodes, so what does it mean? What does a virtual node mean? It can mean taking an entire network and collapsing it down to a single touch point for management, and a lot of commercial products exist out there to say, okay, you don't have to, if you're going to update the network configuration on each node in your system, you don't have to log into the CLI for each of these things necessarily, and type commands at each and hope that they all run at about the same time. You get the single touch point of management. This is one flavor of virtualization. Another flavor of virtualization is address virtualization. So it turns out that everybody tries to use 10/8 internally. It's really useful. And so particularly when you go to multi-tenant environments, who actually controls this? Are there address conflicts at the IP level? You also in the data centers have the same thing at the MAC address level. What is the mechanism that prevents these conflicts and lets these things be managed independently? And current existing solutions look a lot like virtual routing and forwarding, maybe with some MPLS, maybe depending on the context in the layer 2 sense. The VLANs also serve this purpose. These are two different types of virtualization that I feel that people are reasonably comfortable with. And yes, SDN can actually make improvements on these, but these are actually not what I want to talk about today. So what I want to talk about today is what I call policy virtualization. So fundamental in both of these two that's not addressed is who sets the ACLs? If there are multiple paths between a source and a destination, who decides which path is taken? These are policy level decisions. These are totally decoupled from what the topology looks like or what the addresses are involved. So this is exactly what this FlowVisor tool that I'm going to talk about does. And so it will let multiple parties assert different policy on different parts of the network so that you can have multiple forwarding paths in play at the same time for different classes of traffic. And I will throw this out there now. I'm mostly giving this talk without my Big Switch Network startup hat on. But my company and a bunch of other companies have are working on commercial solutions that actually span these different types of virtualization. And also, I should say, I'm hoping that at the end of this talk, we can have a bunch of question and answers. A bunch of questions, and I'll try to answer. But so if folks could hold the questions towards the end, that would be great. In terms of use cases, my guess is that most of you are pretty familiar with at least one or two of these, but I thought it was worthwhile just kind of going through the list of things that I think are most important about virtualization. The big money-making one for a lot of people out there is actually supporting multi-tenancy. And the most common instances are public-private cloud. So public cloud are things like Amazon EC2, where you provide infrastructure as a service, network as a service, or what have you. You accept money from people in exchange for supporting their workloads and their topology. You don't ask them a lot of questions about their workload. You don't say, what IP addresses do you need? You don't say, what MAC addresses do you have? Because in a lot of cases, people don't know. And actually asking them these questions is a bigger speed bump to using your product. And so you really want some level of virtualization. So you don't have to care. They don't have to care. It all just kind of works. So multi-tenancy is a critical use case for virtualization. Another important thing is actually, just like in server virtualization, better resource utilization. So it is often the case, if you think of a workload almost like a little Tetris shape, you could imagine trying to wedge that into part of your infrastructure. But if you put too many shapes in one place, where the dimensions of the shape might be the amount of bandwidth needed, the amount of memory needed, the amount of computational resources needed, if your network is artificially segregated, meaning that you can't just put any piece anywhere, there's not this fluid continuity of networking resources, you can actually have resource fragmentation at a network level. So if you are one of these public cloud provider people or private cloud, as resources come in, as workloads come in, you have to find, where am I actually going to map this into my network? And so quite often what happens is, you've got great server utilization. You can kind of put it anywhere the VMs will let you be. Lots of back-end storage sources, but quite often the network itself is the bottleneck, meaning that if you have network policies, this group of machines is not allowed to talk to these other groups of machines, you might have to pre-program that into every place in your network where those VMs might be. And if that becomes computationally prohibitive because you don't have that many network admins who can't type that fast, and maybe you have network admins that can't type as fast as VMs can move around, which most of us do, then this actually becomes a big problem. And so it gets to the third point is people actually use network virtualization just for simplified network management. You can have network policies that kind of migrate around with VMs. You don't have to necessarily pre-provision these things. And this is, in my mind, one of the most critical but subtle points is that you can decouple policy from topology. So quite often, people have a policy that any traffic egressing from my network, I need to run it through this list of firewall checks. And so how do you implement that policy? Well, you actually put the firewall as the bottleneck point. And that works great. And so now, by topology, you have enforced this policy statement that all traffic egressing must go through the firewall. And what happens when the place that you're egressing actually turns into another tenant of yours? And now that traffic is no longer going through that firewall because it's actually turned from north-south to east-west. Right? This actually, a lot of people we're talking to actually just simply cannot accept certain tenants because their traffic is going from north-south to east-west. And this is a big problem. And another problem that people have not quite hit on yet, but something we've actually run into with FlowVisor, which is why I like it as a use case, is actually multi-layer delegation. So you can imagine that in a multi-tenant network, you give service to some customer, and they might want to transitively give service on to someone else. They might have a value add. And so these are all very interesting use cases for virtualization that I'm not going to talk about too much in this talk. The one I am going to talk about the most is FlowVisor, and FlowVisor uses a whole bunch of tricks to do what I call rapid service deployment, and the critical part of that is strong isolation. So you're going to be able to put using FlowVisor, you can actually put new things into your network with some confidence that if that new thing, if it's experimental or whatnot, and if it goes crazy, will not take down the rest of your network. So you can think of this, much like with server computing, you can install a VM and with some confidence know that there's strong enough isolation that if that VM is compromised or what have you, that it won't take out the rest of your infrastructure. So this last one is the use case that I'll be focusing on with FlowVisor. But at the same time, I want you to keep the rest of these use cases in your mind as we go through this discussion. So FlowVisor actually started as a project for academics, much like with OpenFlow and as with OpenFlow in general, and it has kind of come a long way in this time. And so as I go through these slides, I want you to keep in mind that yes, some of these things might have academic-leaning spins to it, but at the same time, a lot of this can very easily and very readily be applied to service provider networks, to data center networks, to real production networks. And so the fundamental problem that FlowVisor was trying to solve is it's actually really hard to deploy new services in your network, to decide if a service is stable, decide if it's worthwhile. And so by service, I really mean something that requires a change to switches and routers. So either it's a configuration change, or maybe a firmware change, or maybe you've got something even more complex. And so imagine you're an IT manager and you're a network manager, and your boss comes to you and says, I want you to deploy IP multicast. Most of you in this room would probably go, well, I mean, it should work. All the docs say it works. I'll bring it up in a test network, and if it passes that test network, hopefully it'll work everywhere. I'll just deploy it everywhere and cross my fingers. Right? I mean, this is the modus operandi, and this is a real problem. And so it's not just this one thing. It's any new type of routing protocol, any type of monitoring service, all sorts of things fall into this category. And the fundamental thing is that this is actually a really bad barrier in both directions. It means that there are things that are actually really good and useful that don't get deployed because people are concerned that it's not safe, it's not stable, it might hurt the network. And the other problem is that there are things that do get pushed through which do hurt the network. So the barrier is kind of bad in both directions. So if we want to understand why this is hard, if we look at what real networks are, real networks are big boxes, closed systems, lots of complexity here, and that complexity is typically hidden from an end operator. And if you look at the network as a whole, which is, if you've never seen this picture, it's kind of fun if, a little bit simplified. This is a graphical visualization of trace routing from one spot to everywhere in the network. So the real network is actually, closed, and actually it's really complicated. And if I click forward, it even has, and the real complication on it is actually it's populated by real people. And real people kind of do weird, tweaky things, and they have strange configurations. And the net result of this is that trying to guess what's going to happen in this network is actually very complicated. But so what do we do when we go to test new services? So we deploy them on software switches. We have kind of contrived topologies that we put together in the lab. And we do our best to kind of emulate people, but generally we're faking them, we're simulating them. And there's actually a huge jump from something that works in this testbed style space, which what we typically have, to the real network. And in practical terms, that jump is just too big. So what I did, and I had a lot of help in this, is we created this network virtualization. Note, I do say network slicing here a lot, and so honestly, the reason why I say network slicing instead of network virtualization is exactly for that glossary slide. So many people have so many different ideas of what virtualization is that I just gave up and just coined my own term. And so every time I say network slicing, I really mean the specific type of network virtualization that FlowVisor does, and I don't want to argue about it. And apologies for that, because I will bounce back and forth. But the idea is a network slice is a coherent collection of resources in the network. The data plane is totally unmodified. All we're going to do is actually intercept control plane messages. And as you can guess, this is heavily dependent on OpenFlow. And some of the critical properties of the system is that there's no forwarding plane performance penalty by using FlowVisor. And this actually works. It's deployed, and if your boxes support OpenFlow, you can actually run FlowVisor and have this work in your real production networks. This works as a transparent virtualization layer. Each slice believes it has complete control over each switch in your network. The critical thing is that it actually enforces isolation between these slices. So if one virtual network goes crazy, gets compromised, or is just buggy, there actually is enforced isolation so that the other slices can continue to operate. The other thing that I mentioned is these real users. And so this is actually, I think, one of the most interesting parts of this story. So imagine you have this network. Forget about the details of how it happens. We'll get into that in some length. But you have this network where you have different forwarding policies. How do we decide as a user which forwarding policy to use? And so probably your network administrator would say, this is the default forwarding policy. But there's nothing that really stops him from setting up a web portal or something like that, and so that would let you change your forwarding policy. And so the kind of the use case that we're thinking of in an academic environment is a grad student spins up a network slice that, with his own custom forwarding protocol. It's a BGP++ or something like that. And he runs his own traffic on it and only his own traffic. And then he sends an email to a couple of his lab mates and he says, I think this is stable enough. Do you want to give it a try? And so they mail the network administrator, they use the web portal, what have you, and they say, can you switch my traffic over to Brandon's new BGP++ forwarding service? And they give it a try. Some of them decide it works, but it's not that useful. They're going to switch back. Some of them actually decide this actually is really useful. They see performance benefits. And what's nice about this is right with network virtualization, we actually get this really interesting ecosystem of if you create a new service, you can get new testing people because it provides value. And if you're thinking about this with a service provider hat on, these could be customers and this could be a payment portal. So if you're actually providing a new service, so I have accelerated web downloading. You could actually provide this, enter your credit card, enter your customer number, give it a try. If people don't like it, they can switch out. And so you can imagine that this could be even more complicated than all of my traffic, right? You can have customers who say, I want my web traffic handled by the web optimized download thing. I want my voice traffic optimized by the low jitter traffic. And maybe you'd come up with better marketing terms for this. I'm just an engineer. But when you say, and I want the default slice to handle everything else, you actually have this nice evolving ecosystem. You almost have this marketplace for network services. And as long as these isolation properties hold, you actually have this nice system for people to build on and use. So what does a slice policy look like? So a slice policy, it says, this network is allowed to use these links, these switches. Along these links, it can have this much bandwidth. Here's the maximum number of forwarding entries that you can use per box, and you can imagine this getting fairly complex. Here's the amount of CPU on the switch and router that you're allowed to use. So as a detail that we haven't quite gotten into, OpenFlow operations, like any operation, take up amount of CPU. And you can imagine, as you're sending information down to the switch, you could actually send too much. And you could actually generally service other processes on there. And so FlowVisor takes these all into account. But these are kind of course, this is what network virtualization has to think about resources. The one that I think is actually most interesting is FlowSpace. So which sets of packets does this slice control? And so it's actually easier for me to think about this graphically. So if you imagine almost a space across all of the packet headers. So right now I showed just 3 dimensions here where we have all possible MAC addresses, all possible IP addresses, and all possible TCP ports. I only picked these 3 because going past 3 dimensions is actually pretty hard to draw and visualize, but kind of work with me. So you can imagine that there's this green slice which gives you all of the TCP ports of a certain port, independent of whether it's a MAC address or IP address. And so you can imagine in a service provider network, this could be the slice that handles SMTP, the email protocol. And if you were a end user provider, you might say, okay, no one in the residential service is allowed to send mail, and everybody in the commercial service is allowed to send email. And so that might be the policy of that green slice. But what you've said now is that everybody in that slice, for that traffic, is managed by a different forwarding policy. And then one of the vertical bars is a specific MAC address and a specific IP address for all of their traffic. And so that could be a grad student with some new crazy routing protocol. And then the other two bars are the same, but they've got an extra person to join. And so that would be sending all of your traffic. And also, if you look very subtly at the picture drawn in, I don't know if Masayoshi Kobayashi is here, but he spent hours getting these shadows right. There's actually, it's a partition. So the pink actually cuts out the green. So for the intersection there, the pink wins. But for the blue, the green wins. So you actually have this, it's really a partition. There's not an overlap. So the high-level idea is you can actually, along all of the possible headers described in a packet, you can actually chop up your network to divide who controls what. So how does this crazy thing work? So this picture should look reasonably familiar from Brandon's slide. So if you imagine we had an OpenFlow controller on the top, an OpenFlow-enabled switch or router on the bottom. I've actually drawn the inside of that to show the OpenFlow firmware and the actual ASIC. And between these two, we're speaking the OpenFlow protocol. So this should be what you've taken from Brandon's talk. So what we're going to do actually is slide in a virtualization layer. And so the FlowVisor is effectively a transparent OpenFlow proxy. When I'm not feeling very generous about it, I call it NAT for OpenFlow. It's kind of the same idea. So we have the switch on the bottom is talking to the FlowVisor as if it was the only controller in the network. And then the FlowVisor is, again, speaking OpenFlow back to controllers, saying, hi, I'm a switch. And so what happens is, as messages come down from controllers, the FlowVisor actually inspects them and potentially rewrites them or squashes them to ensure isolation. So let me delve into this a little bit more. So if this is the setup that we have, and we have three controllers kind of managing just this one switch, we'll talk about multiple switches in a second. But so if a packet shows up, the OpenFlow that doesn't match any rules in the existing in the existing switch. For example, if the switch was just rebooted and had no rules, the switch would say, I don't know what to do with this packet. Let me ask the controller. So it sends this message up to the controller that it knows about, which is the FlowVisor. And the FlowVisor does a policy check and says, for packets of this form, let me go through my slicing rules and see who controls this. And so it decides, based on the rules that it's been configured with by the person who owns that switch, that this particular type of packet is controlled by Kathy. And so Kathy then turns around and says, OK, I know what to do with these packets. I'm going to insert a forwarding rule that says send this out port number 5. And Kathy sends this down to the FlowVisor, thinking that that's a switch. The FlowVisor, in turn, does a second policy check. It says, Kathy just asserted a rule. Is Kathy allowed to do this? If no, can I rewrite this to what I think Kathy actually meant? And so a common case is Kathy says, delete everything. I'm going to start again from scratch. And this gets rewritten to delete everything that Kathy's allowed to control. So once that rule has actually passed FlowVisor's check, it's actually pushed into the switch. And then the critical thing here is once the rule is in the switch actually forwards packets at full line rate. So, and the other thing is, so I mentioned this as the packet coming up first and then the rule coming down second. It doesn't at all have to happen like that. So in fact, Kathy, if she knows what rules she wants in advance, can actually push those totally decoupled. And so this is what Brandon was talking about in terms of proactive versus reactive flow insertion. So another way of looking at this is if you're thinking about writing an OpenFlow controller, this actually, having this virtualization layer in the middle makes no changes to any of the architectural implications of writing an OpenFlow controller. You could still do all of the points that Brandon had along his space, his little graphs with the slider charts. You can still hit all of those points independent if there's a FlowVisor or not in the way. So in an effort to put our money where our mouth is, so it's actually no longer my personal email and web traffic, but for at least 2 years, my personal email and web traffic actually went over a FlowVisor network. This is a deployment out of Stanford campus, not too far from here. 15 switches, 25 plus users. These numbers are actually increasing, and this is actually one of the smaller FlowVisor deployments right now. But maybe even more brutal on the network than my email traffic was actually 7 different grad students worth of demos in various states of disrepair and bugging and crashing and whatnot. So it wasn't so much that yes, the network was able to handle my email. It was able to handle my email while there were all these other crazy experiments going on. So you might want to take me at my word, but 7 grad students en masse effectively approximates a Byzantine attack. I mean, this is reasonably rock solid. FlowVisor was picked up by a National Science Foundation initiative called Genie. The idea was to actually try to build a end-to-end, but where here the end is actually defined as coast-to-coast research infrastructure for grad students to do wide-area networking experiments. And so what we have is networks that are FlowVisor, OpenFlow-enabled networking devices at each of these sites, all talking to FlowVisors that you can actually talk to and reserve the resources on. And when you reserve the resources across all of these things, you actually get a unified end-to-end slice. And so FlowVisor is actually one part of Genie. Another part of Genie is actually being able to get the associated compute resources. So you can almost think of this as a early stage wide area EC2, except in terms of the networking resources, you actually have OpenFlow control instead of EC2's security policies. So you can actually update the forwarding rules on the fly in an OpenFlow sense, in addition to just getting other resources. I should also apologize. There have actually been a bunch of additional projects, including Ophelia in Europe and some work in Japan that are following the same model. I just don't have slides for them. So this is becoming a larger and larger research network. And to my point about graduate students and availability, the fact that this is able to stay up and stay going means that it might be OK for some production use in non-research and academic networks. I'm going to quickly breeze through what it looks like to use the FlowVisor, just because ostensibly there's some engineers here. There's actually documentation. There's a daemon that runs that takes a configuration file, 3 main commands, the actual daemon itself, a configuration tool that works offline, which does a bare minimum functionality, particularly like changing your password if you forgot it. And then the main configuration tool is FvCTL, the FlowVisor configuration tool. FvCTL actually speaks an API to the FlowVisor, so this is actually just an incredibly poor user interface. And the expectation is that as this becomes more and more popular, people actually will use the control API rather than the command line tool. And I should also thank Ron Milford from InCenter for letting me steal his slides on these particular points. But what does it mean to create a slice? So for the command line, you run FvCTL create slice. You give the slice a name. You give a URL to a controller. It's the person who owns the slice. This is where their controller lives. Threw in an email for contact information, so you know who to yell at when they're, yes, there's isolation in the network, but still you want to be able to contact people when they're doing bad things. And so, an example would be, create a slice for the financial department. This is where the controller lives, and this is their particular network admin. Once the slice is created, you add rules for what is the traffic that they can control. Remember, I was calling these things FlowSpace. So FlowSpace takes the form of DPID, which is a unique identifier for a switch. So on this switch, with this priority, this class of traffic is allowed to do these things. It is the way to read this. And so the particular example here is on the switch, with that hex label, which I won't read for you guys. It's allowed to control all traffic coming in off of port 22. the flexibility of the match structure. So this is actually even an incomplete list. You can subdivide the traffic, if you remember that kind of graphical picture that I drew, by incoming ports, by the VLAN, by the MAC addresses, IP addresses. You can even put insider prefixes there. Network protocol type, is this UDP, is this TCP? Diff-serve addresses, TCP ports. There's full documentation on this in the man page. The reason why I kind of draw out these level of details is that you can actually create some really interesting service couplings on top of this. So one of the examples that we did was a network experiment didn't want to actually handle ARP, it didn't want to handle DHCP, it only wanted to handle traffic for a certain port. And so by cutting the network out just the right way, we could actually have a slice, the production slice, that provided all of the base level network connectivity, the ARP, the DHCP, the DNS. And for the person doing the high level service, it was just a video streaming service. All they had to do was handle the data parts of the video streaming service. They didn't have to spin up this whole infrastructure to manage their network. So we actually have this multiple layers of services, if you will, because these services are not complete silos. They can actually build on top of each other. In terms of the permissions a slice can have, it's actually possible to, the default one that you would think of as the write permissions. This slice can actually direct this traffic through the network. You can actually create a pure monitoring slice with FlowVisor that says, this other slice here is not allowed to direct traffic, but it can make queries about the network. You can imagine for a network administrator trying to manage the entire network. And maybe even more interestingly, this slice can't necessarily do anything itself, but it can delegate to other slices. And the delegation model, which is a bit dodgy if you look at the code right now, but we can work on that. It allows you to delegate a subset of your permissions. So if you've been given all the permissions to do everything, then you can delegate that off to someone and actually say, all right, well, they're only able to read the network on this part for this particular slice. You can list information about slices. You can change information about slices. You can list them. You can delete them. You can list the addresses. Interestingly, and this ends up being incredibly useful for network debugging, you can also get lists of, the FlowVisor actually internally builds up a list of the network topology itself. And so if you are debugging a controller, and particularly you're debugging its topology inference algorithm, you can actually get a little bit closer to ground truth by asking the FlowVisor. This is also useful if you're trying to figure out what subset of switches to give to a slice. But so that actually kind of finishes up the use case for FlowVisor style network virtualization. And I wanted to jump back up a little bit and think about maybe a little bit about the broader picture. So something that FlowVisor does, which people continually question and re-question, and I think it's ultimately was a good decision, but something I think it's worth pulling out, is that FlowVisor actually chooses to use OpenFlow as both the southbound and the northbound interface. And this ends up being very subtle, but critical in its implementation. So you can imagine, and there are actually implementations of people who do this. You can actually do virtualization in a switch, meaning that south of the OpenFlow layer, you have some sort of custom, I'm a vendor, I know how to best virtualize my switch virtualization technology that does exactly what FlowVisor does. You could say, I'm going to create slices of the network, and in fact, there are commercial products right now that do this by VLAN. You can say, for this VLAN, I want it controlled by that controller, and for this VLAN, I want it controlled by the other controller. You can also do virtualization inside a controller itself. So that controller can terminate an OpenFlow connection and then have some sort of internal protocol that people can build on. Maybe I do event passing inside my controller. Maybe there's something, OpenFlow ends up being a very low-level API, a very low-level protocol. Maybe there's something more flexible I can do in a proprietary version once I've translated from OpenFlow to whatever I want it to be. The main reason why I think that it's actually important that the virtualization layer be actually transparent and from OpenFlow to OpenFlow is it lets you decouple the virtualization, which is itself a hard problem, with the forwarding control, which is another hard problem. And so what this lets you do is, for all the controllers that we'll be talking about today, a lot of them came after FlowVisor, but they all work with FlowVisor. And in fact, all the publicly available controllers that I'm familiar with work with FlowVisor, and a lot of them came after the fact. So FlowVisor code stays, on a different trajectory. We work on the isolation. We start working at little bugs here and little bugs there. But this huge swath of controller technologies continues to evolve. And so I think decoupling these things is actually really important for the ecosystem. The other use case that I think is also really important is that you actually get this nice benefit of things being incrementally deployable. So if you come with a great idea, after this tutorial, you get inspired, you go home, you write an application, a controller, you write your own controller or what have you. If you want to test that out, you can test that out in a FlowVisor slice. But once you're reasonably convinced that your great idea really is great, you can actually get rid of FlowVisor altogether and run it natively in the network without changing the code. And so it's both these two use cases that I actually think make it really important that the southbound interface is the same as the northbound interface, and these are both OpenFlow. So I apologize. I was going to do a live demo, and I will try to blame it on the wireless, but it also was a little bit late in coming together. So I'm actually going to show you a pre-recorded demo. So this is the topology that we had at Stanford. This is a video that's available off of openflow.org. We had switches from many vendors. We even had switches that we constructed out of NetFPGAs, which is a different research project at Stanford. And I think my traffic was hanging off of the middle right switch there, but it doesn't matter. So what we did is we took this network and we effectively cloned it with FlowVisor. So each of the clones pictures that you're seeing here are actually different grad students with different experiments. So Nikhil's in the top left, the yellow, was actually a load balancing experiment. The right was a crazy experiment that I would need more time than I have up here to explain, but involved logically spanning FPGAs across a network to create one large mega FPGA. On the blue in the bottom left, there was a video streaming over wireless experiment, and on the right was a wide area network data aggregation experiment, trying to come up with better ways to do traffic load balancing. And the important thing is not, so each of these experiments are interesting in their own right, and if you're interested, I can point you to them. But the important thing is that these were all running on the same network with production traffic. And most of the time, most of my email got to me. And so not so much for a live experiment, but at the same time, I feel like this is pretty compelling. So to wrap up, I zoomed way in on FlowVisor, this network virtualization tool. It's actually, I didn't actually mention, but it is open source. You can download it from flowvisor.org. It's deployed on lots of research and education networks. If you're familiar with Interop, at the conference, it was actually the basis of the virtualization layer for the Interop booth, both last year and will be again this year. There's lots of open source tools. There's lots of mailing lists and whatnot that people can download and use it. But at the same time, it ends up being a very concrete data point for SDN and network-based virtualization, just to help keep some of us engineers honest. And thanks again to Ron Milford for some of the slides. And I guess I'll take questions if folks have them. So let me repeat the question for people who didn't hear it. I mentioned that FlowVisor can divide bandwidth on the links, and what kind of support does it expect from switches? So the OpenFlow 1.0 protocol provides the ability to do what's called minimum bandwidth isolation. So you can give a queue, you can create a queue, and you can assign to that queue, you get at least 30% of the bandwidth. So we're conserving. If more than 30% is available, you get more than 30%, but you're guaranteed at least that 30%. And so I basically make the same assumptions that OpenFlow makes. And as the queues in OpenFlow and the types of services increase, then those can be translated onto FlowVisor as well.
What's the status support for 1.1 or 1.2?
So couple different questions there, and you probably only meant one of them. High level, I'm actually not actively working on this project anymore. I mean, this is my baby, but I've moved on to another company, and so I'm still kind of the front man for it, if you want. I can actually point you to the folks who are doing that. At the same time, there's a little bit of a chicken and egg problem, is that it will only become a priority once there's OpenFlow 1.1 and 1.2 controllers and switches. And so at the same time, I mean, in my spare time, and I try to say it with a straight face, I am trying to work towards that. I'm sorry, to what?
So it could take minutes to merge all the TCAM entries on all switches. So just having a crazy guy has no clue about networking, just changing some rules for his equal traffic to produce a network outage for 10 to 15 minutes, and he has no clue and he don't have any insight if his rules will ever make it to the hardware. So by having the slicing, how do you ensure that you have resource allocation for your different slices not overload?
So let me give you a short answer, and I can point you to the paper for the longer answers. The FlowVisor has there's a couple different resources that end up being the bottleneck there. One of them is actually the CPU on the box. And so we actually go into some fairly big detail for how to figure out what are the sources of load on that and try to isolate them in different ways. So one of the big ways of causing load on that CPU is to actually send more OpenFlow messages. So we actually track the CPU on the box and actually rate limit for each slice how many messages it can send. Now you get to an interesting corner case is with a single message, you can actually cause a disproportionate amount of CPU load. And so for people who aren't necessarily familiar, you can think of TCAMs from a software sense as being a sorted list stored in an array. And if you were to make a pathological insertion between, if you have priority 100 and priority 200, and you want to insert something at priority 150, but there actually isn't space there. So these things are you actually have to do the TCAM equivalent of a mem copy. And so a single insertion can actually cause a disproportionate amount of load. A bunch of the switches we are working with actually have hardware support for this, so that's not a big deal. There will always be, if not this one, but something like that is possible to cause load on the system. And the reason why I say always as opposed to kind of hand-waving my way around it is if you look at the maturity of compute hypervisors right now, there's always kind of the pathological thing that you can do. If you aren't familiar, I can point you to some of the detecting if I'm in a VM or not security work that's done. There will always be these things. And so the question is, how serious are they? How serious are they in terms of how common are they, and then how much damage do they do when they happen? And at least in the case of virtualization, the argument, compute virtualization, the argument is, they don't happen often enough that you can't build a business around them. And so while this code written by me over the course of 2 years is not quite that mature there, the claim is that given enough time, such a thing is possible. Did you have a follow-up question?
So the problem with CPU resources is because then you just hit a CPU limit and it's still continuous, it's just slower. The problem with TCAMs is if they're exhausting the TCAM resources,
Yeah.
maybe forward all packets you don't have any enforcement anyway. Or are you dropping all traffic or you're punting all traffic?
So if you remember on my earlier slides, one of the resources that is allocated to the slice is the number of TCAM entries, right? So you have, much like memory allocation, you have a bunch of different possible schemes. FlowVisor currently implements the stupidest one, which is, every slice gets a maximum number of X. And, X is not a function of the number of slices, so you actually, you can have a limit, whatever your X is, that divided by the number of TCAM entries on the switch is the maximum number of slices you can support. But as this gets more mature, you could imagine this getting more useful and more like memory management, because ultimately that's what it is. It's memory management.
So when we're running experiments with
It sounds like a bug, and we should probably take that offline. But at the same time, I mean, inherent to OpenFlow, you're dealing with a decoupled system, right? So if I try to insert a rule, and a packet is arriving that's going to be affected by that rule, there's inherently a race condition for, is that packet arrived before or after that rule has been fully inserted? And my guess is that completely off the top of my head, online in front of 200 people, my guess is that you're actually running into exactly those problems, and that's slightly exacerbated by the FlowVisor because it picks up an extra millisecond of delay going through the FlowVisor. Other questions? Apologies, I only about half heard your question, but I think you were asking about, so let me try and rephrase it, and you can tell me how close I am. FlowVisor is very purposely focused on really control plane virtualization. It doesn't say much about the data plane. And so what does this actually mean for data plane virtualization? Is that some approximate? Yes. So the statement, let me take it from a different tack. So most policy is actually end host based. This end host is allowed to talk to this class of other end hosts. And so if you start lumping end hosts into classes, how the path that they take to get there is not usually part of the high level policy. However, in modern networks, it's usually enforced with the actual topology. Meaning, I assert that this guy is only allowed to talk to this guy if he goes through this firewall, or this load balancing box, or what have you. And so as the two entities actually move around in the network, it actually becomes harder and harder to actually enforce that type of policy without something extra to try to say, okay, well, no matter where this guy is in the network and no matter where this guy is in the network, it always has to go through this other point. I'm not sure if folks here are familiar with the concept of waypoint routing, but different controllers are actually starting to introduce this where at a policy layer, you say, this guy can talk to this guy as long as he goes through this guy, and it's totally independent of topology. It's a pure policy statement. And so that is, if you're happen to do a huge hairpin or what have you, just make it happen. You've decoupled the policy from the topology. Does that answer your question? Multiple controllers for? I mean, that's totally not to overload the term, but totally a policy-based decision, right? So a single controller can actually have multiple applications running it. Apology. If there are other questions, maybe it would be better if we took this offline. One more question? We have time for one more question. And I should interrupt. I will be coming on stage after Brandon's next talk so we can answer more of these questions in tandem. So if you haven't got your question answered now, then we can take this again afterwards. So it was designed to run on servers. It's written in Java. I am told that people have ported this to Dalvik or whatever is the legally unencumbered version of Dalvik these days. So there's actually work on doing this. I'm not entirely up to date on what that is, but it's not impossible. All right, and apologies for people who haven't had the questions answered. Brandon's going to come up and talk more about other applications of SDN. It turns out the world is not just about virtualization. But then I'll come back up afterwards and we can answer some more. And thank you very much.